Спасибо. Доброе утро, дамы и господа. Меня зовут Pawel Moll, and I think it will be better for everyone if I carry on in English. I'm a software engineer. I work at ARM in Cambridge, UK, and I had certain life circumstances made me work with tools for the last good 6 to 10 years. Tools meaning anything from compilers up to performance analysis tools, profilers, and this stuff. Today I'll be talking about debuggers. And let me ask a question. Is there anyone in the audience who never had to use debugger? And don't be shy. I would be really jealous. I would envy you if you never had this force to use the debugger. Well, I don't see any hands, so I'll assume everyone used a debugger at some point of time. So let's start the presentation in a very typical way these days, with a quotation. And usually presentation just used a boring quotation quote from Wikipedia, and a debugger is a computer program that allows you to debug or test other programs. I thought I would use something more spicy. So I've used a quote from a man of great wisdom who once said this. Any idea who might it have been? Yes, Mr. Torvalds himself. It's been a while ago that this discussion happened. It was 2000. I don't think he changed his convictions nor style since. A quick plan of the presentation. We'll start with ptrace, a foundation of any debug solutions in Linux. We'll talk about breakpoints, everything you ever wanted to know about breakpoints, but you were afraid to ask. We'll have a brief chat about hardware, what can hardware do for debuggers, what's required from hardware. And we'll talk about debug symbols and all the stuff that the compiler will generate to make debugger life easier. I've got a set of optional slides which are kind of more destined at embedded audience, people working with embedded systems. We'll see how it goes. If there is a demand, we can go through them or not. So ptrace. It's a system call. Everyone knows system calls in Unix, like in POSIX, like kernels doing open, file open, read, write, and so on and so on. Ptrace is just another one of them. This one, though, has a very special use case. It will be used by debuggers, GDB, by tools like strace, looking at system calls. Also, the dynamic binary instrumentation tools, which is a topic on its own, will sometimes use of that one. Ptrace is a conglomeration of many functions, as most of syscalls are. But the basic description, the top-level description of what ptrace do, as you can read from on the relevant man page, is to establish a relation between two processes in the system. You've got two programs. One will become a tracer, the debugger, so a program that traces the other one, which is a tracee. Nothing more than that. There is just a relation between two processes in the system. The relation is usually built by a ptrace TraceMe command. TraceMe will be invoked by a child process forked by debugger itself. So when you run your GDB with your application, a program that is to be debugged, at some point of time, and then you run it, so you start it or you use run command, GDB will fork itself, the child will execute ptrace-me, and then execv into your process, into your application to be debugged. This creates this relation. You can create this relation between two random processes in the system using the ptrace attach command. Although in a typical modern Linux distribution, you won't be allowed to do this unless you are root. There is a YAMA security module which provides a couple of settings. It also allows you, the system admin, to completely disable this feature. You may completely disable the possibility of attaching to another process in the system. Why, you may ask? The obvious response to this question is security. You will have your SSH agent running as your user in your system, or a GPG, for example, handling all your private keys. You don't want a malware that happens to run as your user as well to be able to attach to GPG or to SSH agent and steal your keys. There is a kind of workaround for effects of this limitation. Process can call the program control syscall with special parameter and given bit to explicitly say who can trace me. This is usually used by crash dump analyzers. If you use Fedora or Ubuntu and your program crashes, there will be another one that will analyze, that will display a window and provide a bug report, including call stacks and so on and so on. This is enabled by that particular one. So your crashing application, glibc, at exit function, so the last function being executed in when the program is going down, will set this relation and allow other program to trace me. ptrace will, there is a number of phases of the relation between tracer and tracee. The basic one is just process control. So ptrace allows debugger to stop the program being debugged. Type stop in your GDB command line, and it will either send a seek stop signal to the tracee, or it will use ptrace interrupt command. When you continue, you type C or you click the arrow button in Eclipse, it will use ptrace cont to continue, just to enable to restart the execution of your program. It will have a bunch of inspection commands like getRegs and setRegs, processor register values. It allows you to use info register command, and one of the most useful one is two of the most useful ones are pick text and poke text. It enables the debugger to read and modify the tracee address space. You can inspect memory, as you probably have done with your debugger, but for our use case, we'll use we'll start talking about breakpoints now. And in this particular case, the debugger will use those two commands, pick and poke, set and modify memory content, to read an instruction at the address you want to set your breakpoint. So when you say breakpoint some function, it's actually translated into an address, some value of program counter. The debugger will then read the instruction at this address, save it somewhere on the side, just for future reference, we don't want to lose it, and replace it with something different. It will be either a special instruction. Many architectures, many ISAs define an instruction which is a breakpoint. It's got special connotations, we'll talk about it in a second. Or, in the simplest possible case, it will be just an illegal instruction, undefined instruction. As an anecdote, I can just say that our instruction set defines an undefined instruction. If you look through the ISA, through the manual, you will find a set of instruction encoding that is guaranteed not to be ever used. So this instruction will always be treated by a processor as undefined instruction. So we have replaced an instruction in our program, right? And your processor is happily checking through the instructions. At some point of time, it will start executing. It will try to execute this, either the special instruction or undef. What happens then? In all the cases I know of, it will cause an exception of some sort. Interrupt is one of the typical exceptions you will incur in your system, but illegal instruction is another one of them. What it looks like from my user point of view, if you have just executed a program normally from command line that happens to have an undefined instruction because your file has been corrupted, for example, you will see the program dying with seek ill. The message coming from the kernel will be something about illegal instruction executed, program died, potentially core damped. This is exactly what will happen when the processor starts executing this special or undefined instruction. When your hardware supports the breakpoint instruction and your kernel implements the all relevant support, you will get a seek trap, special signal reserved for traps, for breakpoints of sort. If not, you will simply get a seek ill. And now we are getting to another part of the special relation between tracer and tracee, between your GDB and your program in your application. Normally, a signal like seek ill, illegal instruction, would simply kill your process. When there is a tracer is enabled and attached to a tracee, the application being debugged will simply stop. It won't die immediately. And the signal will be kind of passed to the debugger. The debugger will will use the wait-pit system call to obtain information about what's going on with the application being traced. So it will be told that this application, this process, has just executed an illegal instruction. And now the debugger can do a number of things. the most obvious thing it will do is it will go through the list of breakpoints it knows about, because it did set them previously, and check whether the program counter, the address of this instruction, of the illegal instruction, is one of the known breakpoints. If so, it will suppress the signal, so it will make sure that the application won't die in a second, and it will do something else that we'll talk about in a second. This kind of breakpoints is called usually a software breakpoint. Some people like to call it a memory breakpoint because it is being set by modification of memory. I dislike this term because it's very confusing when it comes to watchpoints that we'll talk about in a second. One implication of the way we are setting the debuggers that you can think of is the fact that you can, if you wish so, you could replace every single instruction in your program with a breakpoint. It is possible. And there is actually kind of application for it. I will talk about it later. The only limitation is pretty much the amount of RAM you have for your tracer. GDB, obviously, when replacing the real instruction with the breakpoint, will have to save the instruction somewhere on a scratch memory and also remember an address where the instruction lied. So you can imagine that if you replace every single instruction in your program where code is 100 kilobytes long, you will need something like 300 or 400 kilobytes for the data structure describing your situation. Because that's the way that the software debugger, then, and there are also implications, because we are modifying program code in kind of real time. We are actually mending the instructions the processor will see. We are making sure, well, again, we are causing the every single thread of execution. If you have 4 processors executing the same code in a multi-threaded program, behave exactly in the same way. So every single thread will hit the same breakpoint. There are circumstances when you don't want that. You want only a given thread to hit a breakpoint, and there are solutions for it. We will be talking about it later on. But the sole fact that you are actually modifying live program can be dangerous. GDB is pretty solid these days. You won't see this kind of problems anymore. But in the past, it did happen that a GDB set a number of breakpoints in the program and then died itself. The tracer disappeared from the system, leaving the tracee, the application being debugged with illegal instructions. And the obvious result of it was that the moment when the illegal instruction was executed, this time the program really died. The more exotic implication of that fact, of the fact that we are modifying the program content, is cache behavior. Certain architectures, x86 is not one of them, ARM is one of them, is not so-called ID side coherent. So by modification of a program means modification of data memory from the program point of view. Processor will start fetching those instructions at some point of time, or it may have already fetched this instruction, so it may not see the data change. So the debugger will have to actively maintain cache. Again, GDB is doing a pretty good job there. It wasn't the case in the past, not always. And the even more exotic and, say, embedded or security-related side effect or implication of using software breakpoints is the fact that we need write access to the program memory. We are modifying the content of memory. In embedded systems, where sometimes program is executed directly from flash, which is pretty much read-only memory for this use case, or in a highly secured system when your program code, text sections, are mapped as read-only, so malware cannot modify the programs of the content of the program, it simply won't be possible. So now, we have executed our illegal instruction. There is a simple example here. So we have got 3 instructions in a program executing that normally would look like instruction 1, 2, and 3. Our program and our processor executed 1 instruction before the breakpoint. It then did hit the breakpoint, causing everything that we've already discussed, so an exception, the debugger taking over control, and so on and so on. And now you want to press, you want to type continue, you want to just carry on with program execution. What will happen? The debugger will first temporarily replace the breakpoint with the original instruction. So we still haven't executed it. It will so-called single step through the instruction. So we'll talk about details in a second, but it will make sure that processor will execute that single instruction and then replace it with breakpoint. You can see there is a lot of hassle. There is a lot of things the debugger has to do in order to make it work. So there are other options. In certain circumstances, GDB can allocate some extra scratch memory in the TraceMe program space, and it will use it to execute this instruction. Remember, debugger will have control over program counter. It can change the program flow if it wants to. So instead of just ping-ponging this the original area of memory with the original instruction, it will just use the copy that it's keeping somewhere else to single step through the instruction. Now, single stepping is actually harder than you think it would be, because if you think about the approach that we've taken about the breakpoint being just an instruction being replaced, you have to know what the next instruction is, or the next source line is. So the next instruction, next GDB command will execute the program until the next source line is being hit, and we'll talk about optimized code, where effects of that particular approach can be interesting. Or next instruction, next I, means machine instruction, but in certain circumstances, it's actually quite hard to calculate the next instruction. On x86, for example, instruction can have different length. And you have to know the address of the next instruction. So first you have to decode the current instruction to see how many bytes are taken by the instruction, and then you can only replace the next instruction with breakpoint. In case of thumb instruction set on ARM, we have conditional instructions. So we just in runtime, as we go through instructions, we can just skip some of them. And again, debugger will have to decode the couple of instructions, understand which one would be executed or not, and replace one or more instructions with the temporary debugger. The hardware, debug hardware, as we'll talk in later on, can make this process much simpler. Now, I've already mentioned that you could potentially replace every single instruction in your code with a breakpoint. And there is a hypothetical scenario for it. GDB these days can do so-called reverse debugging. So instead of you normally would have next instruction, but you can also have previous instruction. Sorry. And the previous instruction will do exactly what you think. It will move backwards in time. There is no magic, processor cannot do it. So in the simple possible use case, GDB will single step through every single instruction in your code and will record its state. So it will record what was the state of registers at that particular point, and it will just rewind it back. There are other options that this one is quite expensive one, so your normal program execution will be slowed down by a factor of 100 or 500 times. Other approaches to the problem usually based on some kind of tracing. You can either have a software tracing, so we will have additional agent in the system that will translate instruction and insert instrumentation, but it's a completely separate subject, hardware can provide tracing features. It used to be the domain of embedded systems. These days, even x86, your humble x86, will have processor trace built in. And the breakpoint, the last thing I want to talk about breakpoints is conditional breakpoint execution. Think about your debugging a loop that takes 10,000 iterations, and something is going wrong in the middle. You will not probably single step through 10,000 iterations. It will be quite time consuming. So the usual approach to the problem is to make sure that your breakpoint in your loop is only executed every 1,000 times. So every 1,000th time a breakpoint would normally be executed, the program will be stopped. That's what we will do, setting a break with some condition if iteration if I modulo 1,000 equals 0. The problem is that actually the breakpoint is always taken. It's just that the GDB will not pass control to you every single time. It will only pass control to you every 1,000 times. So this will also introduce overhead. There are ways of mitigating it, and GDB for the last couple of years provides an alternative to conditional execution for that particular case, which is called tracing. it will, instead of stopping every thousandth time in a loop, it will save your requested context somewhere in a trace buffer, and it will just execute it automatically. And again, in the basic implementation, it will still take the breakpoint every single time, only save the trace record every thousandth iteration, but it can be mitigated by injecting even more code into your trace application. So GDB can inject a special shared object, special library into the TraceMe address space and use it as a launchpad. So instead of replacing an instruction with a breakpoint, your requested instruction with the breakpoint, it will branch to its own shared object. And then it will have a JITed expression that you have, the condition that you have asked for. It will reduce the overhead of such approach significantly. It is also on the verge of, this approach is also on the verge of so-called dynamic binary instrumentation techniques. You may have heard about Intel pin. You have very likely have heard about Valgrind, or Valgrind, depending how you pronounce it. That's where the lines are becoming a bit blurry. What GDB these days do quite often is very similar to what tool like DinInst, which is another approach to dynamic binary instrumentation, would do. I encourage you, if you were into such subjects, I encourage you to have a read about the DBIs. DinInst, Dynamo Rio, Valgrind, Intel pin. Those are the headlines, the topics that you would like to investigate. Now, with talking about ptrace, we have described what operating system has to do for a debugger. Without ptrace, so without any support from the operating system, the debugger simply wouldn't work, at least not in the way that we kind of used to it. Every single operating system has some kind of a support for debugging. This can be made, and its life can be made much easier by small portions of additional silicon. Your processor will take that much space, for example, and then there will be additional area here that will be dedicated only and only to debugging. And this is the silicon our friends in silicon design hate it, because it does not bring the benchmark results up. They are being kindly asked by marketing people to make the benchmark results better, to sell more processors. And they will invest the silicon area, so they will implement additional things in the hardware in order to bring the benchmarks, the scores up. And then people who would like to actually use those systems come and they say, right, but we need we'll have a problem. We'll need to debug some portions of our code. So the processors will usually invest, the designers will invest some time and effort into making the processor more debugger friendly. They will, usually the system, the hardware will allow something called, especially in embedded like processors, will enable halting mode debugger. And we can talk about later on, but what it gets down to is that you are completely stopping your system execution. The clock is not ticking. Then some external entity, it's usually a separate machine wired up somehow to the main one, can tick the clock, so can make sure that only single instruction has been executed, or even to greater extent that only part of pipeline is being progressed. But that's a kind of a big hammer solution. What the hardware can do as well, in the simplest case, is to make the single stepping that we've already discussed simpler. There might be a special processor mode that will make sure that only single instruction is executed, and we don't have to go through all the problems of finding out where the next breakpoint should be and so on and so on. It's usually as simple as setting a set of registers. The debugger will make sure that the TraceMe will only execute one instruction and nothing more. This is quite often related to hardware breakpoints and watch points that we'll talk about in a second, and the significant part of debug hardware is quite often related to tracing, that I've already mentioned. It's a completely separate subject, and a big one as well. So, hardware breakpoints are pretty much implemented pretty much as a comparator. So there is a logical comparator, like your TTL logic that will look at program counter and compare it against a pre-programmed address value. The moment when those two match, an exception will be raised. Again, you would see it as SIGIL, illegal instruction, or SIG trap if the kernel supports it. The trick here is that there is a limited amount of such comparators available in your hardware. I've already mentioned silicon is expensive. You will get 4, 6, 16 if you're lucky. Meaning you will not be able to set a hardware breakpoint on every single instruction in your code. That's impossible. Now what you can do, and that's how usually single stepping is being used, is a reverse approach. So hardware breakpoint described as stop your processor if program counter is different than the given address. And single stepping in this, you can implement single stepping very easily using that particular feature because you know what instruction you want to single step. You make sure that the comparator will fire when PC is different, you set the PC to this address, and you start the processor. Processor will execute this instruction because it is equal to the address that you have set, and it will stop immediately after on the next instruction. That's the usual implementation of the problem. From the low-level point of view, the debug logic will be usually controlled either by special instructions, or, like on ARM, for example, it will go through a special ptrace instruction command, HB, hardware breakpoint preferences registers, which is actually implemented in perf event code. There were some good or bad reasons behind it, but perf is involved in debugging as well on Linux. A special variant of a hardware breakpoint is a watchpoint, which is sometimes called memory breakpoint, not to confuse it with software breakpoints. Again, this is a comparator, a limited number of them. The difference is that they will look at data bus. So instead of generating an exception when instruction is being executed, it will generate an exception when some kind of a memory access, a load, that's one of the options, or store, writing to memory, or either of them is being executed. And this requires hardware support. Short of full binary translation, you cannot implement it using any software means. So without hardware support for watchpoints and operating system implementing it, you won't be able to use watchpoints in your code. Let's talk briefly about debug information or debug symbols. I assume that people here will know that executable in Linux is usually comes in ELF format. Debug symbols, debug informations are just additional segment or section of this file. Sections will contain text, program code, data, and so on and so on. There will be a section called debug info, .debug info. And data in this section are formatted according to a dwarf standard. Dwarf actually has some meaning, and I always have to use notes because it's completely pointless. It means debugging with attributed record formats. The truth is that it has been the resolution has been kind of retrofitted, and the original intention of the people naming the system was to relate to the elves. They were clearly fans of Tolkien. If you use object dump, that can decode the debug info sections, you will find a number of records like this. Just a couple of examples from my simple test code. Compile unit, compilation unit, you can think of it as a source file, a.c. That originally lived in my home directory, and the instruction generated by the compiler for that particular compilation unit live between address 836C and 7E. There's a couple of them. Subprogram, another one, is a function. That's kind of, if you translate dwarf lingo into a human language. The name of the function is A. Yes, function A in file a.c. I wasn't particularly inventive at the time. And if you look at the addresses of this function, you will figure out that it's the only function in this file that has been compiled. And by the way, it will contain some additional information like the version of GCC that was used to build it. The other set of debug information is one that is probably the most kind of understood and known one, is debug line section that maps machine instructions into your source code. If we get back to my example here, a.c file will have 3 source lines, and each line will be compiled into some set of instructions starting at the given address. If you do the math, you will see that some of the lines will, by the way, this is thumb instruction set, so instruction is either 2 or 4 bytes long. So if you do the math, you will see that each line will generate 1 or 2 instructions. So the difference between those addresses will be 2, 4, or 8. And it's simple. This code was built without any optimization whatsoever. The moment you start using -02 or -03, interesting things happen. If you ever tried stepping through optimized code, you have seen the kind of highlighting line in Eclipse or the arrow in command line GDB just going all over this place. The compiler will optimize out symbols. So a function that you want to set breakpoint of is unknown to the compiler, to the debugger, because compiler optimized it out and forgot to tell the debugger about it. The variable is missing, basically on the same basis. The jumping back and through is usually related to code reordering or folding. So the compiler will transform the C code and generate interesting set of machine instructions. Inlining, very common optimization. Some instructions will have some lines will have no machine instruction related to it, so we won't be able to set a breakpoint on this source line. Some source lines, some machine instruction will have more than one source line related to it. C++ templates are particularly notorious here. They are very long, and they magically compile to pretty much nothing. If you look at this example here, it's Drystone. If you never heard about Drystone, you have to be worried. It's about 20 or 30 years old benchmark that is completely meaningless today and still loved by marketing guys. Meaning that the compilers are usually quite good in compiling Drystone. It does not necessarily transform to normal programs. So anyway, if we have a look at the short part of the Drystone debug information, and you will start at looking at the addresses, machine instructions, you will see that those addresses again are consecutive. That's the order in which the processor will execute instructions. Now, if you look at the line numbers, so there was 6, 8, C, 1A, 22, and so on and so on. Now, if you look at the line numbers, you will see how our cursor, the highlighted line, goes all over the place. We started with dry1C in line 196. Next, we ended up in a header file. Then we got back to the same line in dry1C. Then we went to line 210, then 382, and so on and so on. That's the effect you will be observing. And the last thing I want to talk about related to debug information and the behavior of the debugger is call stack. Something that is very often requested by in bug reports. My simple code here is not particularly inventive. I've got 3 compilation units. You've already seen the A.C. Function A will call function B and modify its result, returned result. Function B will call it C, and so on and so on. So now, if we stop here, we will set breakpoint at line 5 of C. We'll see that call stack, backtrace, as it's also called in GDB. We are in function C, line 5. We got there from function B, line 5. Okay? And we go to B, we got from A, line 5. So far, so good. Everything works. The way it works is branch, or jump to another function, normally. Call will save return address on stack and change the program counter. So, unwinding the stack, or stack walking as it be usually called, will simply go through stack frames. It will have to know where the stack frames are. It's a longer story how to fetch them, and I can talk to you about it later if you catch me on. But the bottom line is it's also non-trivial. The problem is that it's not exactly reliable. The moment I've enabled any optimization in my example, the compiler noticed that function B, the return value of this function, is dependent only and only on the result of function C. It's not modifying at all like the A, for example, is. Meaning, the compiler will be clever-ish, and instead of issuing a call instruction, the one that would save return address on stack, it will just do a normal branch, unconditional branch. Meaning, the return address to this function is not on stack. So walking stack will not reveal the fact that B was on the call chain, on the call path. That's what you will see in a debugger. That's why I like to call the call stacks return stacks, because they don't show how did you get to a function, what was the call path. What they show is how will you return from that function. not widely understood but quite important phenomena, especially when it comes to analyzing how did we get to the buggy condition. All in all, just to summarize all the issues that I've already mentioned, is we call what the debugger presents to you as a programmer a debug illusion. What we think is happening is just a simple, straight thread of execution. Unfortunately, because of all the factors they've already mentioned, it's quite biased. It's a well-known optical illusion that you should see those lines being bent. And that's exactly what's happening with debuggers. They provide you with illusion. Those are the embedded subjects that I can go through if anyone wishes so later on. But I want you to remember a couple of messages here. Number one, operating systems and hardware must support debuggers. It's not always debugger's fault. Sometimes the hardware is broken or the operating system is faulty. The debug hardware is expensive, therefore it will be limited. The debugger will only show what the debug symbols will tell it. So sometimes it's just simply a compiler's fault. GCC was not always great in generating debug symbols. It's much better these days, but it still got some shortcomings. Because it's actually pretty damn hard to generate proper debug symbols for highly optimized code. And last but not least, do remember and do treat the backtraces with limited trust, with a pinch of salt. And now, as a closing remark, I wanted to use another quote, this time also from a very important person in the Unix era. This one slightly more polite than the other one. You may have heard about it. It was the fundamental paper by Brian Kerrigan about Unix, and there was a section about debugging there. And he concludes saying that, generally speaking, the best debugging tool is your brain. Okay, plus a couple of printers. Thank you.
Thank you very much for your excellent presentation, and we have about 5 minutes for questions.
Thank you again for your talk.
My pleasure.
You have mentioned PIN, the dynamic program analysis framework from Intel.
Yes.
Does the ARM have something similar?
Yep. So we, starting from the Valgrind that I've already mentioned, Valgrind already works today. It's using a different approach than PIN is doing, because it's doing full binary translation rather than just instrumentation as PIN is doing, meaning the overhead will be larger, but it works. Now you've got DNIST, it's already working on AH64, and our equivalent of PIN, and using very similar techniques, is an open source project currently maintained by Google, and that we are working on as well. It's not, you won't get it for AH64 yet, you will get it for 32-bit ARM already, and it's called Dynamo Rio. Dynamo Rio. I will write it down around here. Or I'll write it down later for you.
Okay, thank you. The next question.
Yeah, I had a question about the optimization and debugging optimized symbols. So the main problem with optimized programs is that they crash when you don't expect them. And when you try to insert a couple of print statements or any other way influence the code itself, it won't be optimized the same way, and it won't crash at all. So when you try to debug it, you will see that some variables are not accessible because they're optimized out. So how do you battle that?
Unfortunately, Brian Kerringam's approach is the only real answer here. Or tracing. Tracing will give you an ultimate insight into what was going on during the program execution. I have no silver bullet for you. There is no magic tool that will help. Number one, obviously thinking, and number two, if you really need, if you're really desperate, then have a look at, well, on x86, Intel PT. Perf can help you with that.
Thank you. Next question.
Hi.
Yeah, works.
Yeah. So my question is, you talked mostly, I think, about debugging user space.
Yes.
What about kernel? What technique is used when we are using KDB or KGDB?
So the opening quotation that I've mentioned from our friend in Linux Foundation was actually related to KGDB. With that, the people were trying to get KGDB, which is so-called GDB stub. That's one of the kind of embedded subjects here into the kernel. It actually got in 10 years later in a completely different shape and form, but it's there. So we've got four main techniques. Five actually. Technique number one, and my favorite, is printk. Technique number two, and that one that is actually useful, very, very useful, is TracePoints and ftrace, okay, which is pretty much like printk. Technique number three is KDB, which is like magic scissor request, and you will get a command line inside the kernel, and you can do basic operations, data inspection, and so on and so on. This one works. It's not particularly useful in my personal opinion. Now, the way that most of the embedded tools are using the KGDB that I've mentioned. KGDB is like GDB server in user space. It will take remote commands from your Eclipse or GDB command line, send over TCP, serial line, and so on, and then it will do pretty much the same operations that we've mentioned inside the kernel, including breakpoints and so on and so on. And the fifth approach is JTAG, where you use the halting mode debug that I've mentioned to stop execution of the kernel and then single step or modify the kernel code.
Thank you. A couple minutes for the last question.
And by the way, I'm around, so feel free to stop me at any point of time.
Thanks for the talk. I have also the questions related to the kernel and
Sure.
KGDB.
KGDB, yes.
Yeah, exactly. So, is it possible to use hardware breakpoints if, for example, the kernel is executed from Flash, so without using software breakpoints?
I cannot answer you off the top of my head. You can set software breakpoints in kernel by modifying the code. Now, the answer to your question is another question whether it has been implemented. So as I say, the hardware breakpoints registers are usually controlled through a perf interface, and if someone worked on wiring up the KGDB interpreter into perf hardware breakpoints, then it will work. If it doesn't, patches are welcome. I simply do not know. It would be entirely possible. I see no technical reasons why it wouldn't. I simply don't know whether someone implemented it or not.
So okay, and this functionality, is it available on Cortex-M series?
Very specific question. I think it is. You will have very limited. You will have extremely limited set of resources. I think you will have a 1 or 2 comparators. I will check it in TRM. So ask me in 15 minutes time, and I'll give you an exact answer. But I think it is.
Okay, thanks.
Thank you very much.
Thank you.
The next presentation will be here in 10 minutes.